Log on, tune in, find out. Another good idea from Cambridge.
That's Alessandrini, and he's going to talk on the inverse crack problem.
Thank you, Chair. And thank you to the organizers for giving me this opportunity to speak to this audience and in this magnificent institute. So, the topic of the talk is the inverse crack problem, and my principal aim is, rather than talking of some few new results which are available, to advertise some old problems which have been remaining there unsolved for a long time, and hoping that some fresh idea comes out and something is done. So let me start with the basic situation. So the idea is we have one body in three-dimensional space, and within this body there might be a fracture which is modeled by a regular portion of a regular surface which is orientable, and so this surface is okay, doesn't matter, I use this one. This is the surface which models the crack, and what one would like to do is taking electrostatic measurements from the boundary of the body to determine the presence and the shape of the crack. So the direct problem in its most elementary setting can be as follows. We have an electrostatic potential which is harmonic into the body, except that on the crack it has zero flux on the two sides of the crack. Of course, here nu plus, nu minus denote the unit normals pointing to the outsides of the crack on the two sides. And for instance, a current density is prescribed on the exterior boundary of the body. The inverse problems would be to determine sigma given boundary measurements of the potentials for a finite number of potentials corresponding to given current densities psi 1, psi k. Of course, this is only one of the many various formulations that are possible. One variant which has been very popular in the past, and I will come back to this later on, is the model of a so-called perfectly conducting crack. A perfectly conducting crack is not a fracture. It's a surface which is made by material which is perfectly conducting. And so the potential rests to a constant on such a surface. So this is a model which is not very much physical, but we will see later on that it is very much related to the previous one, and a number of results are available for this problem. And next to that is the model of a crack with impedance, that is the zero flux condition on the two sides is relaxed with the addition of this term. So we assume that on both sides of the crack Robin type condition is given. So we admit that there is some loss of energy when the potential gets to the crack. And the loss of energy is represented by these two functions which are positive, non-negative or positive. Of course, one model which has been considered, and the one for which the better understanding is available by now, is the two-dimensional model. This is also essentially an abstract situation, but the picture is clear in this case. So in this case, omega is a two-dimensional body, and the crack is represented by a simple curve. Another variant which has been considered with with the several results is the one of what are called the multiple cracks. That is, sigma is not just a single portion of the surface, but it is the disjoint union of several cracks, which are regular orientable surfaces. And one other thing that has been considered is the case in which instead of having only finitely many measurements, which seems to be on a dimensional ground the reasonable way to do, is to consider the set of full boundary data. That is, either to consider the Neumann to Dirichlet map, as in this case, or equivalently the Dirichlet to Neumann map. A final variant that I will mention is the one in which the body is not, the body of omega in 2 or 3 dimensions is not homogeneous, but its inhomogeneity is known, is given. And so in this case, the underlying elliptic equation is not the Laplacian anymore, but is, for instance, this divergence equation with a variable coefficient, but known. So let me just briefly review what is known in the two-dimensional situation. There is one fundamental paper by Friedman and Vogelius who proved the basic uniqueness result. But let me list 3 fundamental facts that can be learned from that paper. First of all, they observed that at least 2 measurements are necessary to uniquely determine a crack. This is very well explained in the following term. If you choose any harmonic function in your domain and you consider any arc which is a line of steepest descent of this harmonic function, this could be a crack for the same boundary data. So given boundary data which correspond to a harmonic function do not permit to distinguish a crack from the empty set. And so one measurement in general does not suffice. But instead, if one chooses carefully, and I will say later on what this carefully may mean, 2 boundary data, then the corresponding measurements suffice to uniquely determine the crack. And the third fundamental fact that was observed in this paper is the duality which occurs between the perfectly insulating case and the perfectly conducting case. The duality comes from harmonic conjugation. And so for practical reasons, it is often convenient to switch from the insulating case to the conducting case just using harmonic conjugation. And then soon afterwards, in the year afterwards, also the multiple crack case was considered, still in 2D, first by Brian and Vogelius, then by myself with Diaz Valenzuela, and simultaneously by Kim and so. And the final result is the following, is that also for the multiple crack case, assuming that the cracks are a finite in number, no matter what their number is, 2 suitable measurements suffice to get the unique continuation, the uniqueness of the crack. And then also the stability issue was considered, and starting with a paper of mine in '93 and ending with a paper of Rondi a few years ago, the final result is that the mapping, having chosen suitable boundary data, the mapping from the data to the crack is continuous with a logarithmic modulus of continuity, provided some a priori regularity assumption is made on the crack. And the final result by Rondi is that, in fact, a very mild regularity assumption suffices. That is, it suffices that the crack is a simple arc which is Lipschitz. And what is known also is that this logarithmic modulus continuity is best possible This was shown in a paper of Di Cristo and Rondi, in which they presented a wealth of counterexamples for several inverse boundary value problems, which have this logarithmic continuity as the best possible one. So let me talk of what is available in the three-dimensional situation. There is a paper, a relatively old paper by Kubo, who essentially showed that if one assumes that a crack is contained into, it is flat, it is contained into a plane, then one can choose three boundary data so that the crack is uniquely determined. Essentially, the idea is if I take boundary data which correspond to three linear functions which are linearly independent, say x1, x2, x3, then the boundary data corresponding to that uniquely determine the crack, provided it is flat. Then, some years afterwards, Eller proved uniqueness assuming full boundary data. And in fact, Eller considered the more general case of the impedance crack, the crack with impedance. Then there is a paper by myself with Emanuele Di Benedetto in which we obtained essentially three results. First of all, we showed uniqueness for conducting cracks in three dimensions, that is, surfaces which are conducting in three dimensions, with two suitably chosen measurements. And then we were able to prove stability with a different argument only in the case of a planar crack. And for the case of insulating crack, we were able only to prove uniqueness only in the case of planar insulating cracks. So what are, let me say, at least in my view, what are the main open problems which remain to be treated? Let me start with this one first. Probably this is not the most important, but this is the one that I will treat later on. So the results that I have mentioned in the 3D case all concern the case of a homogeneous medium. The inhomogeneity is not considered in that case. And so, of course, the results of uniqueness in the three-dimensional case are still incomplete in the homogeneous case. So, at least for the moment, these questions is relevant only for the conducting case. Then, what I believe is perhaps the most important and most interesting open problem is the one of uniqueness for an insulating crack in 3D with finitely many measurements, of course. And the point is find a clever choice of such measurements. And the third one is the one of stability, and this will be the last one I will discuss later on. So let me talk a bit about the first of these problems. So let me tell more precisely what is the uniqueness result that was obtained in the paper with Di Benedetto. The suitably chosen measurements in this case are a very crude model of a two-electrode configuration. So we fix three distinct points on the boundary, and we consider two current densities which are concentrated with a positive charge at P, the first one, and a negative charge at Q1, the first one, and the second current density has the positive charge at the same place as before, and the negative charge is moved. So this practically it seems very nice. Of course, having delta function is maybe not practical from a physical point of view, but in fact this result could be adapted also to the case in which these delta functions are replaced by characteristic functions of small sets. And so the corresponding potentials uniquely determine sigma. Of course, I will not review all the steps of the proof of this result, but so the question is this one: can I extend this result to the case of inhomogeneous media? What is behind the proof of the Di Benedetto paper? There are several steps. One is this one, and this, I believe, is the one which is most challenging to be extended to the inhomogeneous situation. What is the situation here? We have a regular surface in R3. So let me give a short picture. So we have a three-dimensional domain. I have a surface which I call S, and this is a regular surface. And I assume that on this surface I have one harmonic function which is constant. So U is constant here. And then I have a portion, a smaller portion of this surface, which I call S prime, and on which there is another harmonic function in all of omega, which is constant, maybe with some other value, B. And then what is evident in the case of harmonic functions by analytic continuation, if this is the case, then we must have that V equals identically B on all of S. So that is, there is continuation along a level surface of a harmonic function. So this is the problem that I have been trying to advertise for years, but I don't think there have been any progress in this. Can we extend this type of result to solutions of an elliptic equation with variable coefficients, not necessarily analytic? So we have one elliptic operator. I assume here some regularity on the coefficients because I believe that at least the minimal assumptions in order to have the standard unique continuation for solutions would be necessary. And so we have two solutions. We have one regular surface on which one of the two solutions is constant. The second solution is constant on a smaller portion. Then we would like to know whether it continues to be constant on all of the surface. So what I have to do with they're just two solutions. And the only relation that we know is that V is constant on a smaller subset of a level surface of U. Sorry? No, because this solution V is constant on a set which has to be part of a level set of another solution. That is, this bigger surface must be related somehow to the operator. And the relation that I claim is that this is a portion of a level set of another L harmonic function.
So in other words, the difference is S level U minus V.
Yes, of course. In the case, I have stated here with C and B because in the case that there are lower order terms into the operator, subtracting constants may not be allowed. But if you are considering only, it would be, I believe it would be a very much interesting problem also in the simpler case of principal part operator only. That is, just with the divergence term only. In that case, you can construct constant, subtract constant, and you can say that this is 0 and this is 0. But if you want to consider something like the Helmholtz equation, then you need to have constants there, unknown constants there. Okay, so this is what I wanted to say about this first open problem.
Is there any known case other than harmonic case?
I don't think so. Besides equations with analytic coefficients, of course. If you have analytic coefficients, solutions are analytic, and then you can use analytic continuation. So let me pass now to the case of insulating cracks in 3D. In order to understand what is the problem, let me start first with the situation in the two-dimensional case. So I have rewritten here the direct problem. And the point is that what we can prove in 2D is that we can find a wealth of choices of pairs of current densities, psi1 and psi2, such that if I consider not a single solution but the pair of solutions as a map, then the Jacobian determinant of this map is nowhere 0 in omega except sigma. This is the crucial point of the result of uniqueness in the two-dimensional case. So the obvious question is, can we do something similar in 3D? Can we find, in this case, the translation of the result would be changing from 2 boundary data to 3 in order to obtain maps which have a target in the same dimension as the domain from which we start. So can we find triples of current densities such that the corresponding harmonic map has the Jacobian determinant non-vanishing everywhere? And we would like, of course, we would like to have this result independently of sigma. That is, this triple should work whatever sigma is. Now, in order to understand why the two-dimensional result works, it is better, I believe, to recall a fundamental theorem, a very old theorem, which somehow is attributed to Radot, but in fact proofs were due to Kneser and Choquet, in which cracks do not appear at all. So the theorem is as follows. One takes a simply connected domain in R2 and a convex domain in R2 as a target. And one considers a boundary homeomorphism which maps the boundary of omega onto the boundary of this convex set. And so one has a pair of boundary data. In this case, these are Dirichlet data, not Neumann data. But that doesn't really matter. And then I consider the map whose components are harmonic and satisfy the Dirichlet condition. The theorem which was claimed by Radot and immediately after proved by Kneser is that in fact this is a homomorphism of the whole of omega up to the boundary to the convex target. And in fact, once we know that this is a homomorphism, this is in fact a diffeomorphism, because there is a theorem of Hans-Levy which tells that if one has a harmonic map in 2D, which is a homeomorphism, then in fact it is a diffeomorphism. And so one gets also this non-vanishing of the Jacobian, which is the fact that we need for the crack problem. So this is a picture of what happens in 2D regardless of the presence of the crack. So it would be necessary to have something like this also in the three-dimensional situation even before we introduce the crack. If we cannot do it without a crack, there is no chance that we can do it with the crack. So what is the known situation in 3D? There are only counterexamples. There is a relatively old counterexample by Wood which tells that the Levy theorem fails in 3D. That is, there are homeomorphisms which are not diffeomorphisms. There is an example by Melas which tells that we can find a homeomorphism, so it maps the boundary onto the boundary of the ball. It is also a homeomorphism inside, but at some point the Jacobian vanishes. That would be not so bad in the end, but what is really bad is this example, actually a family of examples by Laugesen, who showed that one can find homeomorphisms of the boundary of the ball into itself, which are close as much as we like to the identity in the uniform norm, such that the corresponding harmonic extension is a mapping which is not one-to-one. So in this case, what happens inside is that the mapping folds itself. There are surfaces on which the Jacobian determinant vanishes. The Jacobian determinant changes its signs. So it's a dramatic situation. So what is the lesson, however, that we learn from here? What we can tell is that to obtain harmonic maps which are diffeomorphism in terms of their boundary data is not impossible. It must be much more difficult than what happens in the two-dimensional case. That is, to find a recipe to obtain that is not forbidden by this result, but such recipe must be very much complicated. So for the purpose of the cracks, in fact, it would be sufficient to have a little bit less than non-vanishing Jacobian everywhere. What would suffice is the following. So it would suffice to find boundary data such that no matter what is sigma, and for any regular surface away from the crack, at least one of the three potential is such that the normal derivative across this surface is not identically zero. If this is the case, then one gets the uniqueness result. You can imagine that this S might be a portion of a different crack to which the same boundary data correspond. And so, of course, if this is a different crack, this normal derivative should have to be zero. And so this can be reformulated as follows. So here is again the boundary value problem for the perfectly insulating case with three different current density which need to be chosen, and we want to choose such current density in such a way that the set in omega minus sigma where two things happen. The Jacobian determinant vanishes. That is, we admit that the Jacobian determinant may vanish, but if this occurs, then the Jacobian matrix itself applied to the gradient of the determinant is zero. Well, what we want is that this set is not too large. It has at most dimension 1. Of course, these are harmonic functions, and so these expressions here are all analytic. So dimension for this set has a natural meaning. And the point is the following. If the determinant, the Jacobian determinant vanishes on a surface, well, and if this surface is regular, is a surface on which the Jacobian determinant changes its sign passing across it, then it's normal, the normal to this surface is given, has the direction of this gradient here. So what we want is that the normal derivative of at least one component of this mapping is 0 on such surface only on a small set. If this occurs, then we have uniqueness. So the challenge here is to understand these objects in terms of the boundary data. So this is the problem, and I leave it to the audience. Okay. So how much time am I left? Stability. Of course, the stability problem with finitely many measurements in the 3D case is not the appropriate time to do that, because we don't have enough information about the uniqueness, so it's out of our scope by now. So what we can consider at present is to consider the case in which we have a full boundary data. That is, to translate the uniqueness result by Eller into a stability result. And this is what I've been doing with Eva Sinčić, which is here. And the result is the following. Assuming some a priori regularity assumption on the crack, the map which associates to the full Neumann to Dirichlet map, or the Dirichlet to Neumann map, this doesn't really make any difference at this stage here, to the crack has a logarithmic modulus of continuity, which is, in view of the Di Cristo-Rondi result, the optimal result. Because in fact, this I forgot to mention, the examples by Di Cristo and Rondi prove optimality or logarithmic stability, not just for finitely many measurements, but from the full boundary data. So let me just tell a few words on the approach. The approach is based on the method of singular solutions. So this is a very well-known method in inverse problems. I don't know if I know the origin of it. I know that I have learned it from Victor, from his paper in which he considered the problem of transmission. That is, one has a conductivity with a jump, and one wants to determine the jump from the Dirichlet to Neumann map. And he proved the uniqueness in this case using singular solutions. And in fact, also the result by Eller of uniqueness that I have mentioned before is based on an approach which uses singular solutions. Singular solutions have been also used in many ways for stability. Here is just for sure an incomplete list of results. It can be used in particular to getting boundary values of unknown coefficients in inverse boundary value problems, and in some cases also interior values. And then it has been also used for problems like the one of Isakov in order to get stability. This was done by myself and Di Cristo for the inclusion problem in the elliptic setting. This was extended to a parabolic setting by Di Cristo and Vesella. And Di Cristo has also done work with applications to inverse scattering using singular solutions. But of course, singular solutions are pervasive in inverse problems, and also reconstruction has been also in reconstructions. And here I just mentioned two starting points, the probe method by Hehata and the point source method by Podcast. And then there have been a long sequel of results afterwards that I cannot mention here, but they basically use singular solutions as a main tool. The other tool that we need is an identity which may relate the difference of two maps when we have two different cracks, sigma 1 and sigma 2, in terms of what's happening inside. This is a kind of identity which is which occurs in many situations in inverse boundary value problems. The difficulty of obtaining it in this case, contrary to what happens, for instance, for the standard conductivity equation, is that if I take U1 to be a solution corresponding to the crack sigma 1, this is not a suitable test function for the problem for the crack sigma 2, because the test functions for a given crack are functions which are h1 minus that crack. And so if I take U1, this is h1 minus the crack sigma 1, not the crack sigma 2. So it takes some time to obtain this identity. It involves a careful use of integration by parts. Of course, it's nothing else than that, but it is a little bit troublesome because we have to use integration by parts in omega minus the two cracks. And if I remove one crack from one regular crack from a domain in R3, I still obtain a relatively nice domain to do integration by parts. But if I remove two, I may obtain something which is very wild. Oh, this intersection is not allowed, sorry. This is not what I wanted to do. Sorry. So there may be cusps of any kind, and the number of connected components may be wild, and many strange things may happen in this case. So it requires some care to obtain this identity because of this reason. What is the result? Well, in the end, we get, on the right-hand side, we get integrals on the portions of either one of the two crack minus the other, or the common portion integrated with respect to two-dimensional surface measure in case this common portion has a positive two-dimensional measure. Otherwise, this third term cancels. And within the integrals, we have some terms in which the two potentials occur, and occur also the necessary jumps on the potentials which have, for instance, U1 and its normal derivative may have a jump on sigma 1. And so here we have the jump of this one. U2 and its normal derivative may have a jump here. And on the common part, both of the two have jumps. And so this is what we get. And then the next ingredient is to introduce an appropriate Green's function. Of course, we have Robin boundary conditions, so this will be the Robin function. And it is convenient to introduce a Robin function not precisely for the domain omega, but for one which is slightly bigger. And so I have a delta function on the right-hand side as usual. I have the homogeneous Robin condition on the crack, and essentially homogeneous condition on the exterior boundary. This is placed here in order to balance the presence of the singularity. And the point is that if I pick points y and w, which are in omega tilde, in the bigger domain, but outside of omega, then, and I fix the second argument of R1, for instance, this is a nice solution for the crack problem with the crack sigma 1. And this is a nice solution for the crack problem with the crack sigma 2. So I can use these two solutions within the identity that I have written before. So, and this is the equation that appears, this is the identity that appears here. I have also added some simplification because of the Robin conditions where I had written before normal derivatives. Here I have the jumps of the impedance term only. But let me come back a little bit. Now, let me look at the right-hand side that I have here. Here I have a function of two variables, w and y and w. And if I take y and w away from the cracks, this is a harmonic function, separately in y and w. So I consider this function here, and this is a harmonic also when y and w move into omega. The only point is that they have to be away from sigma 1 and sigma 2. And so I can use the harmonicity of this function with respect of the two variables separately. Now, in the case that in which I have the identity that I have shown you in the previous slide, then because of the identity, I can estimate this function here in terms of the difference of the Dirichlet to Neumann map. So if these two maps are closed, this is also small, provided y and w are in this layer here. And then I repeat what I have already said. F is separately harmonic in these two variables, and so this allows me to use estimates of unique continuation starting from point y and w, which are outside, and carrying them inside. I may obtain that also these functions here are small even if y and w get into omega. I'll come back to this in a second. And then the last ingredient is the following. If I take a point of sigma 1 which does not belong to sigma 2, just looking at what happens here and knowing what is the singular behavior of the Green's functions, I can estimate the blow up of the function capital F as y and w tend to this point of sigma 1. Because in this case x belongs to sigma 1, so we are looking here, and when y and w tend to a point of this portion here, then this term here, actually this does not blow up much. This is the principal part. This is the one with the true normal derivative. This is a normal derivative that cannot be cancelled by the Robin condition because R2 is regular. This is not part of the boundary for R2. It is not regular, but we know exactly what is the asymptotic behavior of this term. So the point is to combine these three ingredients, and from the ingredients we get an estimate of the Hausdorff distance of sigma 1 from sigma 2. The delicate point of this is the fact that it is troublesome to do harmonic continuation in this set here because of the reason that I have said before. This is a wild set. It is disconnected. So we can do a harmonic continuation only on the connected part which touches the exterior boundary. And we can do a quantitative continuation only on nice part of this connected component, because if there are cusps or even worse bottlenecks, it may be difficult to get estimates. the additional ingredient that we need to use is the a priori regularity of the cracks. If the two cracks are regular, then we can estimate their Hausdorff distance in terms of the distance of those points of one crack which are outside the other but are nicely reachable from the outside. This is a quite technical geometric argument, but not so deep indeed. And so, putting together these three ingredients, what we get is what we expected, that is the logarithmic stability. So I think I will stop here. So I wish to thank you. I finish with a picture which has not much to do with what I've talked about. This is an example of a cracked body which does not satisfy the a priori assumptions.
Questions?
Just a small comment. You said that perhaps conductive cracks are not that interesting, but I think in geophysics they find cracks that are filled with salt water that would appear to be very high conductivity.
That's interesting. Thank you.
Questions?
This question may not have anything to do with the crack detection, but suppose in 3D, suppose there's a harmonic map, and you know that there is a homeomorphism on the boundary. And in addition to that, suppose you know that the Jacobian doesn't vanish at all inside. And does it follow that it is a diffeomorphism?
Yes, I think so. There are theorems of global invertibility that tells that.
More questions? Yes, not. So let's thank the speaker again.